In this video, I'm going to try and make hypothesis tests for the slope parameter make a little bit of sense. Uh, a lot of students just find it to be a a set of calculations that you have to do, and then you have to remember exactly what the correct interpretation of these numbers is. And I don't want that. I want you to have some intuitive understanding of it. So I'm going to try and give that to you in this. Hopefully that goes well. So we're going to go with some made up scenario where we have some sample of beta hat equals 2.3. And our question is this a significant number? Significant being, is it significantly different from zero? Why zero? Just because if we have a line with a slope of zero, then y and x are not related at all. So this is why we're testing whether or not the slope is equal to zero. It's so that we know if they're related. Uh, a better way to ask this question, and this is going to be important for later, is 2.3 far from zero? So relative to the variance, is 2.3 a big number compared to zero? So we would like to use the population value and just be able to say, well, the population value is this, 2.3 is close to the population value is not zero, we're done. If we knew the population value, we can tell whether it's zero or not. We don't need to do anything else. We don't know that. So this is where hypothesis tests come into play. So we're going to start with the assumption that the population slope is zero. We're making this as an assumption. I want to say the word assumption many times in this video just to be clear. We are assuming that the population has a value of zero for the slope parameter. Now, if this assumption is true, then there's certain possible samples. So in one sample, we might get if we take samples from this population with a slope of zero, just by chance alone, we'll get a slope parameter of 0.8. Sometimes we'll get 0.1, sometimes negative 1.2. Maybe beta hat is 1.6 in this sample. These are, again, we're still in assumption land. These are just possible samples from this assumed population. From these possible samples, we get a sampling distribution. So this is assuming that the slope is zero for the population. We got something like 0.8, which I'm going to put here. We got 0.1, 1.6 is one of the values that we got, negative 1.2, and so on. So in this case, 0 is right here. And we would get, every time we took a sample from this population, we get a different value of the slope. Just the way random chance works, every time you take a sample, you get a different value. But most of them are going to be close to zero, and as we move far away from zero, we see fewer and fewer. So we end up getting most of them close to zero. The probability that one is close to zero is very high. Further away from zero, it's less likely that we're going to see a slope that far away just by chance. So this is why a sampling distribution is important. I realize you can't even see the word. It's a sampling distribution tells us the distribution of all possible sample values under the assumption that our hypothesized slope is correct. So let's tie this back in to our question. Is 2.3 far from zero? I'm just gonna move that there. Well, I'm gonna draw the sampling distribution bigger and a little bit clearer. We've got a value of zero here, and then we've got 2.3 over here. So that's where 2.3 is. So now that we have a distribution, we actually have a sense of scale of this. The sampling distribution, we then scale it down by the standard error, and we can start looking at what is this area? What is the probability of the tail here? So what we're seeing is 2.3 far from zero? We can't calculate the point value of a probability. Probability that the slope is exactly 2.3 is zero, just because it's a continuous distribution. The probability of any individual point is zero, so probability, we talk about area. So the area of the tail becomes our p-value. This area just tells us how likely is it that if zero is the correct slope parameter, if the population has a slope of zero, how likely is our sample? There's a little twist here because we're asking, is it far from zero? So we actually also look at negative 2.3. just because we're looking at how far from zero will we allow. So we have to go far in both directions. So in the positive direction and in the negative, we have to look at both of them. Just a little technical thing there. And then from this, we can actually see if our p-value is small, then these tails are really small, and that means we're really far out the tails. So um, a small p-value means that given that 0 is the population parameter, 2.3 is really far from 0. A large p-value would mean that there's more area in these tails, which means that this distance isn't as large. So a large p-value means it's close to our assumed value. A small p-value means it's far away from our assumed p-value. And this is where the p-values come from. Um, there are a couple important things to note here. Number one, we are making an assumption. It is an assumption that the population parameter has a slope of 0, and based on that assumption, how likely is the data that we got? So this white curve here is telling us that only after we make the assumption are we incorporating what our data was. All of this stuff below the assumption line is stuff we can do without taking a sample. We don't need to know our sample value to know that the sampling distribution of a slope parameter from a population where the slope is 0 is going to be centered at 0 with a specific standard deviation that we can calculate. We do a little bit of math in order to make the sampling distribution fit a t-distribution so that we can find the area easily. And then we see how does our slope parameter compare to the one that we would get if the population had a parameter of 0. So hopefully that clears a little bit up. One of the common mistakes when talking about p-values is we just say probability that our slope is 2.3 by chance alone. That is incorrect. We need to talk about the probability that the slope is 2.3 or larger in either direction under the assumption that the true population slope is 0. So the p-value always depends on that assumption. If we don't have that assumption, we don't have a sampling distribution to compare to. We can't actually find a p-value without first assuming the population has a slope of 0.